Hi guys, it's Talha here again today. So today what we are going to discuss will be about some distributions. So we have already covered our binomial distribution. We have discussed what is a Poisson distribution, and today we are going to discuss what is hyper hypergeometric distribution. Hypergeometric distribution of a discrete random variable. So this hypergeometric two times. Hypergeometric distribution. Sorry for my handwriting here. And after that, after we are done with this, we are going to discuss what is uniform distribution. So this is for discrete random variable, the hypergeometric distribution of a discrete variable, and this is going to be our uniform distribution for our continuous random variable. And after today we are going to discuss these two topics, and tomorrow I'll be discussing our sampling distribution of mean, and how we how we take out samples, statistic from samples, and then we calculate the and then we calculate the distributions of those statistic in order to get some inference about the population. So we are going to do that tomorrow, inshallah. So today, let's first start with our hypergeometric distribution. So first topic is hypergeometric distribution. So we have already studied our binomial distribution, and we have studied our Poisson distribution. The only difference between these two distributions and this distribution, I have already discussed what is the difference between these two, the binomial and Poisson. The difference is when n, or the total number of trials, approaches to infinity, so you use Poisson distribution, and if it's limited, you use binomial distribution. So in Poisson distribution is basically a binomial distribution where your n, or the total number of outcomes, approach infinity. But what is the difference between these two distributions and our hypergeometric distribution? So in these two distribution, the main condition is that your experiment, the random experiment, has to be independent. Means the occurrence of one event does not affect the probability of the occurrence of another event. So for example, in the binomial distribution and the Poisson distribution, we had, for example, if we toss a coin 5 times, or let's not use the tossing the coin example. Let's use the dice example. So for example, if we throw a die uh, 3 times. So for example, in the first time we threw the die, we got 2. So the first time we threw the die, we got 2. Now this 2, the first time we got 2, this 2 is not going to affect the probability of other numbers to occur in the second and third try. Means that this 2 is not affecting, the occurrence of this 2 is not affecting the probability of other numbers to occur in other tries. But for example, if I say that I have a box, and I have four red socks, and I have five blue socks. So I have four red socks, and I have five blue socks. Now, if I say that I am to collect a sample of I am to collect the sample of seven socks, or yes, I am to collect the sample of seven socks, and I am to do it without replacement. So if you do it with replacement, this experiment or this sampling is going to be your independent, because you know you're replacing, so the probability is not going to be disturbed. It's going to remain the same throughout the all the experiment. But in a dependent event in a dependent event, the occurrence of one event affects the occurrence of another event. So for example, if I take a sample of seven, if I take out seven socks, so now out of, so these seven socks can be any socks from the red and the blue. So for example, if I say that I take out the seven socks, and there are three red socks in that, and there are 3 plus 5, and there are 5 uh, blue socks. Now the total number of red socks were 4, and the total number of socks were 4 plus 5, we had 9. So we have 4 by 9, and that's equal to a number. So the total probability of the sample, the total probability that we are going to have for the red socks was 4 by 9. But here, as we took out a sample, and we took out 3 red socks and 5 blue socks, and we are not replacing these socks back in the container. So now the probability of red is not going to be the same. It's so right now we have 1 red sock and 0. In that container we have 1 red sock and we have 0 blue socks. Now the total probability is 1 divided by 1, and now it is 1. So that means there's a 100% chance of the red sock being in the container, and the red sock being selected. There's a total 100% chance. But right here we had 4 by 9. So it's different because we didn't replace socks back in the container. So that is why the chances or the probabilities are so this is a dependent event where you don't where the events, or where the samples, or where the objects don't get replaced. Instead, they just are chosen once, and then the probability of the occurrence of other events differ because are dependent upon the event that occurred first. So that was a dependent event. So when you have a dependent event like this, you use hypergeometric distribution. So its mathematical form, the mathematical form of hypergeometric distribution is your when p of x take the value of little x, you have, this implies this is equal to your a by x, your n minus a, your n minus x, and divided by your capital N, choose x. So what does this mean? So here a is your total number of successes in an experiment. So what is the total number of successes? Let me explain. So for example, you have a box, and you have 4 red socks, as I explained here, and you have 5 blue socks, and you're interested in finding the probability, in finding that what is the probability of selecting. So first we got a sample. So for example, here we have a sample right here, that is three red socks, and we have 5 blue socks. So we have a sample of 7 socks. Okay, let's just ignore this. So we have a sample of 7 socks, and here you have 4 red socks in the population, you can say, and you have 5 blue socks. So here you say the total number of success. For example, you're interested in the number of red socks, and the total sample is 7. So you want to find the probability, that what is the probability that in these 7 socks, in this sample that is of 7 socks, there are 3 red socks. So our the total number of successes means that the total number of the objects you are interested in. So though that is 4. So here our a can be 4, because the total number of successes, or the total number of objects you are the number of objects you're interested in, that is your x, but the total number of that objects in that population is your a. That means the total number of successes, that is your 4, that is red. But for x means, when capital X takes the value of small x, that means the number you are interested in. So for example, there are 4 here, so that is the total number of successes, and you say the n3 is got to be your x, because you're interested in the probability of 3 in this sample, and small n is your sample, which you just took out. In the question is given that you have a sample of 7 socks, and capital N is your total number of socks, means your total population, that is 4 plus 5, that is 9. So if you want to calculate this so let me just calculate it. So if you want to calculate for 3 socks, so you have the formula p of x. When x takes the value of little x, you have that is equal to your a x n minus x, n minus a, sorry, and n minus it's a little hard to remember, but once you get the logic, it will be a lot easier for you to solve the problems and write this and when you write this formula again and again, you will eventually get the logic behind it. So you have n, you have small n. So if you put the values, you remember our a was 4, because we had 4 red socks in total. The total number of successes were 4, and the number of successes we were interested in that total number of successes was 3. So 4, choose 3. We have capital N, the total number of the total population, so the total number of socks were 9. Then we have minus 4, so that means this is success, and 9 minus 4, it's going to be your failure. So this is success, and this is going to be your failure. You have x equals 3, because that is what you're interested in. You have n, that is your sample, that was 7, the sample you selected. X is again 3, and then you have n, the total number of socks, and small n, the sample 7. So once you calculate this, it's actually going to give you the probability of getting 3 red socks in a sample of 7 socks out of 9 socks in total, in which 4 were red and 5 were blue. So by this formula here, you're going to get the total number of with the 3 red socks, you're going to get the probability of getting three red socks in a sample of 7 socks out of 9, where 4 are red and 5 are blue. So this was hypergeometric distribution, where you have dependent events, not independent. So the probability of one event does affect the occurrence or the probability of other events in the same population or sample. So this was about a hypergeometric distribution. Now we are going to discuss what is a uniform distribution. So up till now we were discussing the probability distributions for our discrete variables, but now a uniform distribution uniform distribution is for our continuous variables. So this is the first distribution we are going to discuss for our continuous variables. So continuous variables means that they're infinite and there are no jumping points like we have in the discrete variables. So what a uniform distribution is, so the mathematical form of a uniform distribution is your f of x or equals f of x equals 1 divided by b minus a, where x has got to be greater than or equal to your a and less than or equal to your b. So let me give you guys an example. So for example, if we draw a graph, so we have a graph like this and in a for a continuous variable, the area under the graph is our probability for a certain event. But when we are going to calculate the uniform distribution, so we have the distribution at the exact point is 0, and we are going to prove that right now. So we have here, we can say we have 1, we have 2, have 3, 4 and 5. So we say, so the uniform distribution is actually a rectangle because the probability is same throughout an interval. The probability is always same. So we can say that from 1 to 5, all of the area under this graph is our uniform distribution because it's uniform throughout the interval, that is from 1 up to 5. But once you leave the interval, or once you get out, the probability becomes 0. It falls down to 0, and this is our f of x. So as we learned in previous lectures, that the area under graph or the probability cannot be more than 1. So all of this, if we if we add all of these probabilities, we are actually going to get 1. So uh, so the probability or f of x is going to be 1 by so what you do, you calculate the area of the rectangle, which is base into your height. So the height of this here is f of x, and your so the base is f of x and your height is so the base is here from 1 to 5 and your height is f of x. So if you calculate the base is 5 and your height is f of x. So if you want to find f of x, the whole area is got to be 1 because you add the probabilities and you get 1. So you have 5, and from what number you multiply 5 and you get 1? Well, that's got to be a reciprocal of 5 because 1 by 5 into 5 equals 1. So f of x equals 1 by 5. So here, if you want to find the probability of x when x take the little x, and that little x is 3, or that little x is greater than 3, because it cannot be exactly 3, because I'm going to prove you that in a bit. So you have 1 because f of x was 1 by 5 equals 1 divided by b minus a. So your b is 5, and your a is 3, because you want to to find the distribution, the uniform distribution from when x takes on the value of little x that is greater than 3. So you have 5 minus 3, because if you cut this part out, you get the probability of this area. So 5 minus 3, and you have 1 by 5 equals 1 by 2. When you shift 2 to that side, you have 2 by 5. So that is your probability for when x takes on the value of little x that is greater than 3. So this was the uniform distribution for your continuous variable, and before that I explained the hypergeometric distribution, and in tomorrow's video we are going to discuss the sampling distribution, the sampling distribution of mean, and we're going to take out and calculate different statistics out of sample, and we're going to take out samples to estimate the total population. Alright guys, thank you very much.